Let's talk about some special representations that are used quite often, and these are binary, octal, and hexadecimal. So binary is base 2. Octal is base 8, and hexadecimal is base 16. So when you think about binary, the digits you're going to use are just zeros and ones. Octal, the digits are going to be 0 through 7. But when we think about hexadecimal, I need to get all the way up to 16. And so I'm going to use 0 through 9, and then I'm going to start to use letters A, B, C, D, E, F. So if your remainder, for instance, was a 10, you would use the letter A as your digit. If your remainder was an 11, 12, 13, 14, or 15, you would use the letters B, C, D, E, and F. But what I also want you to notice about these is that 8 is 2 to the 3rd, and 16 is 2 to the 4th. So these are really just powers of 2, bigger powers of 2. And that's going to be important because when I'm converting both of these, all three of these, binary, octal, and hexadecimal, into decimal numbers, base 10, I can use the conversion methods from before. What if I want to convert them in between one another? Well, then there are some shortcut methods. So this table here, which is also in the notes, is going to be an important table. And if you notice in this table, if we look at a column of this table, for instance, 10, what that can show me is that 10, the decimal number, as a hexadecimal is going to be the letter A. As an octal is going to be a 1 and a 2. So remember, if you think about octal, that means 1 times 8 to the 1 plus 2 times 8 to the 0. And as a binary number, 10 is going to be 1, 0, 1, 0. So that's 1 times 2 to the 3rd plus 0 times 2 squared plus 1 times 2 to the 1 plus 0 times 2 to the 0. And so when I'm converting, I can just group things together. So each octal number, octal, is a group of 3 binary digits because 8 is 2 to the 3rd. And each hexadecimal number is a group of 4 binary digits because 16 is 2 to the 4th. Now, you might notice that in some of these examples, like for instance at 5, I only have a group of 3. But if at any time I need to, I can put a 0 in the front, and it doesn't change the value by putting a 0 in the front to make it a group of 4 for hexadecimal. So if I have an octal number or a hexadecimal number and I want to convert to binary, then I'm just going to take each digit, use this table, and convert it to a group of 3 for octal or 4 for hexadecimal. And then the resulting number will be a binary number. So convert the octal expansion. So remember, octal means groups of 3 of 7312 to binary. So I'm going to go to the octal digit 7 and notice that gives me a 111. Then I'm going to go to the octal digit of 3 and notice that gives me a 1, 1. So 7 is going to convert to 1, 1, 1. 3 is going to convert to 0, 1, 1. 1 is going to convert to 0, 0, 1. And 2 is going to convert to 0, 1, 0. So the 7312 base 8 is going to be this decimal, this number, base 2 in binary. When you write binary, normally they group them in groups of 4, so you might want to rewrite this in groups of 4. But it's not necessary. Okay, so how do I go the other way? What if I have a binary and I want to go to octal or hexadecimal? So this says convert the binary expansion of this number 111, 0111, 1010, 1100, base 2 to hexadecimal. So remember, hexadecimal is groups of 4 because it's 2 to the 4th to make 16. So I have groups of 4 here naturally. And what I'm going to do is look on my table for these digits. So 1100, I find it there, which is 14. In hexadecimal, that's represented by a C. 1010, I find it here, which is 1, 2 in octal, or 10 as decimal. I represent that as an A. 0, 1, 1, 1. Now notice there's a 0 in the front, so it's this number here, 0, 1, 1, 1. That's a 7. And then 1, 1, 1, again, they have to put a 0 in the front. 1, 1, 1 is the same, a 7 again. So the binary number, 111, 0, 111, 1010, 1100, binary base 2, in hexadecimal is going to be 77AC.